Well, hello guys. Welcome to the last lecture of CSC498. We are almost there. So what have we been looking at? Well, this entire course we've been looking at stochastic models, and we started off with very basic things, and we got into Markov chains, continuous time Markov chains, discrete time Markov chains. And up until last lecture, basically everything was exponential. We had like a set of usual assumptions that we imposed on things. But last time we began looking at something called the MG1 queue. And that's the queue that, has exponential arrivals. And when I say exponential arrivals, I mean jobs arrive following a Poisson process. The inner arrival times are exponentially distributed, but the service times can be completely general. So we began to relax that assumption on the service times. And I told you last time to maybe give this a little bit of thought, because there's another assumption that we can relax as well, and that's the service discipline. And what do I mean by service discipline? Well, it's basically the policy of how we serve jobs. What order do we serve jobs in? And, we haven't explicitly said it necessarily for every model. Some models we have said it explicitly, but oftentimes we have an assumed service discipline, and that's first come, first serve, or first in, first out. And this is, I think, the most intuitive one, because this is the one we experience in our daily lives, right? You go to the grocery store, you go to the bank, you go to a roller coaster on an amusement park, and everyone has like this, okay, I arrived before this person, therefore I'll get served before this person. But are there other things we can do? And especially in computer systems, is this the best thing we can do? And is it, the best thing from a performance standpoint, and as well from a fairness standpoint? We'll touch a little bit on that. Okay. Well, it's really a bummer that this isn't like a discussion-based course. I'd love to have you guys here, because this is, kind of the fun portion of the lecture. How would you serve jobs and stuff like that? I basically have to just tell you the different ways that we can serve jobs. And that's going to be, I'll just write a couple. So we have first come, first serve. Well, maybe the natural thing to do is to just do the opposite of that. Change the service discipline completely, do a total 180. Well, what's the opposite of first come, first serve? What about last come, first serve? Well, that seems odd. And like there's some spots or some areas, some contexts where you definitely wouldn't want to do that, because there'd be like a social uproar, or people would game the system in a weird way. Imagine if at the grocery store people were served last come, first serve. And then you get to the line, you see someone else approaching the line, you'd be like, you go first, right? Because I want to be served. So it seems like a bad idea. Well, see, it's not necessarily a bad idea. But there are two subclasses of this last come, first serve. One's preemptive, and the other one is non-preemptive. So you might say P or NP, not like P or NP from my other course, but preemptive or non-preemptive. Okay. Well, what's the preemptive versus non-preemptive version? Well, in the preemptive version, if a customer or job is currently being processed and a new job arrives to the system, we stop processing this one, and the new one that arrives gets put in its place. So preemptive is we can preempt jobs that are currently in service. We can kind of pause their service time or pause their processing, put them to the side, maintain the order so we know like who to serve next after we're done. But preemptive basically allows us to stop the current job being processed, preempt it, and let another job be processed. One thing that is going to be true for all of these policies, and I'll just get it out of the way right now, all of these policies and service disciplines are going to have something called work conservation. What do I mean by work conservation? Well, if I'm processing a job and that job is being processed, let's say for 1 second, and let's say we know ahead of time it has size that requires 2 seconds. I mean, we might have that information, we might not, but we process it for 1 second. Then a new job arrives and we decide to preempt that job. So we stop processing that job, we put it to the side, and we come back to it later. Well, when we come back to it later, what's the remaining processing time? It's only going to be 1 second, because we've already put 1 second of work into it we save that 1 second, we conserve the work that's already been put on into it, and we just have to do 1 second remaining. Okay, so first come, first serve, last come, first served, and we have preemptive, non-preemptive. What's something else we could do? And this coffee of mine's eyeing me up. Oh, it's not done yet. Perfect. Well, one policy. What was that? Ah. They aren't broke. That's good. They are falling over. Ah. Good enough. Where was I? Oh, one policy that students often come up with, and they've seen it in their operating systems courses or other courses, even like in 373 we talk about like job scheduling and stuff like that. But one thing people say is, what about some kind of round robin policy? So maybe if I have 3 jobs waiting in the system or waiting in queue, I'll process the first job for like a time slice, maybe 1 second, then the next job for 1 second, I keep cycling it through. You could do something like that, but let's say instead of processing a job for 1 second, maybe we say we process it for half a second, or maybe 100 milliseconds, or maybe 10 milliseconds, or maybe 1 millisecond and start cycling through. Or maybe we process it for like a nanosecond, or a fraction of a nanosecond. And what I'm getting at is, what if we make that interval so small that all these jobs are being processed concurrently, essentially. Theoretically, we can process things concurrently. If you were to implement this on a computer, maybe it's just 1 clock cycle or something like that. But let's do a round robin version, a round robin policy, where the time slice is essentially 0, meaning they all get processed concurrently. So if my server has processing rate mu, and there are 2 jobs in the system, then each of those jobs are going to begin to be processed at rate mu over 2, half of mu. And if there's n jobs, it's going to be mu over n. They each get an equal share of the processor. And what we call that is processor sharing. And this is a processor sharing. That's not how you spell sharing. There we go. So one thing right off the bat, you might say, well, I'm not so sure about performance, but depending on your notion of fairness, you might think, what, processor sharing seems like an inherently fair policy, because at every moment in time, every single job gets an equal slice of the processor. Now, that's not incorrect intuition, and I've seen published papers use processor sharing as a benchmark for fairness, but it might not necessarily be the case, and we can maybe discuss that a little bit later. Okay, so first come, first serve, last come, first serve, and processor sharing. Anything else we can do? Well, what type of course is this? This is a stochastic modeling course. What's stochastic mean? Well, it's just a fancy word for random. We've talked about that before. Well, if we're in a stochastic modeling course, maybe we can do something stochastic. What if we do something random? And what do I mean by that? ROS, random order of service. Why in the world would I ever want to do a random order of service? Well, before I do that, let's kind of consider how this works. So whenever a new job arrives to the system, if there's a job currently being processed, then you preempt that job with a job randomly selected waiting in the queue. And then you start processing that job, and you repeat until, of course, the job leaves. And whenever a job leaves the system, you again select one randomly, or a new job arrives, etc., etc. It seems like a bad idea, but there are a couple cases where it actually is a reasonable thing to do. And to understand why it's reasonable, we kind of have to start looking at different policies. Well, this whole class of policy is I'm getting a little bit ahead of myself because I have one more I need to get through. So let's put a bookmark on what I was just about to say. But there's another policy. It's called LAS. This is least attained service. least attained service. What does that mean? Well, that means at any point in time, the job that we're going to be processing is the one that has so far received the least attention from the processor. So let's say I have a job, it's the only job in the system, it starts being processed, it's got 1 second processing on it. Then a new job arrives, right? Call that job 2. Job 2 preempts it. Because why? Well, job 2 hasn't got any service yet. The job 1 has 1 second of service. So job 2 starts being processed, and when it receives 1 second of processing time, then what happens? Well, the system says, well, okay, job 1 and job 2, they've now received 1 second of processing time. Now we'll start to give them equal share. So essentially, it starts to implement processor sharing. But if at any point a new job arrives while they're being processed, or another job's being processed, it again preempts, and it keeps track of all the service levels of every single job, and at any moment in time it's always going to be processing the job with the least attained service, or processing a set of jobs that all have equal least attained services using processor sharing, if you understand what I'm saying there. Well, all of these policies have something in common, and that is they're not taking advantage of job size information. So these are what we call blind policies. So when it's making its decision whether to process job 1, 2, 3, etc., it's not looking at, well, job 3 has size 6, job 2 has size 10, job 1 has size 2. It's not making use of any of that information at all. These are all blind policies. And you might not have that information available to you, so you might be in a blind situation, in which case you have to use one of these blind policies. But imagine you're in the other case, the other scenario. You have that information available to you ahead of time, or maybe you can at least estimate it. What might be some things you do then? Well, if we have non-blind policies, and we're really just going to focus in on one here. There's a lot of non-blind policies, and you can look at the textbook if you're interested in some more of these things, but there's one that's really intuitive right off the bat. So if we're looking to have good performance, if we're looking to have a low response time, what might we do? What might we do over here? We have job size information available to us. Well, maybe we process the shortest job first. That makes sense. Shortest job first, okay. I can get on board with that. That makes sense. So if I'm gonna have like if I know job size is ahead of time, and I have a 10-second job, I've been processing it for maybe 5 seconds, right? A job arrives, maybe it's just 1 second processing time required on it. That's its size. It has a size of 1 second if you can kind of put a time value to the size value. You say, okay, well that 10-second job, that's gonna be preempted by the 1 second job. I'm gonna do the shortest job first. And that makes a lot of sense. I like that idea. And it's probably pretty good for response time, expected response time, higher moments of the response time, etc. But let me give you another scenario. What if, let's say I have that same 10-second job, right? And I've been processing it for a certain amount of time. And a 1 second size job just arrives. Now under here, I'm always going to preempt that 10-second size job. But what if that 10-second size job has been processed for like 9.9 seconds, okay? And then that 1 second job arrives. Should I preempt it then? Well, think about it. If it's a 10-second job, it's been processed for 9.9 seconds, it only has 0.1 remaining processing time to clear the system. If I preempt it with the 1 second job, I then have to wait 1 second for a job to leave the system. So perhaps an adaptation or a little modification we can make to this shortest job first. Maybe we don't just look at the absolute size of it, but how about we do shortest remaining processing time? Okay, Well, that kind of takes care of that case I was just talking about. And it seems like it's going to be, at least as good as the shortest job first in terms of performance, but it might offer some problems. Same with shortest job first. Okay, well, for the remainder of this section of the lecture, this part of the lecture, I'm going to basically hit you with some facts. And I'm not going to show you proofs of this. Proofs are in the textbook if you're interested. Some of these things are going to be intuitive to you. Some things are not going to be intuitive. But I'm going to show you some things, and we'll take a look at these, different policies. When might they be a good idea? When might they not? So check this one out. An MM1Q distribution. So when I say distribution, I mean number of jobs in the system. An MM1Q's distribution is independent of its service time for blind policies. Of its service time distribution. What am I saying? Not service time distribution, but it's service discipline. It's service policy. Is independent of its service policy. If the policy is blind. So if we don't know precise job sizes ahead of time, and none of these service disciplines know job sizes ahead of time, then an MM1Q's distribution for the number of jobs on the system is independent of its service policy. What does that mean? Well, one consequence of that is the expected number of jobs in an MM1Q using first come, first serve. And I'm just saying expected number of jobs in an MM1Q for first come, first serve equals the expected number of jobs in an MM1Q using processor sharing, for instance. And this is just a consequence of, it's the entire distribution. This is just the expectation of it. But of course, that's going to equal same thing for last come, first serve, preemptive or non-preemptive. It's going to be true for random order service, and it's going to be true for least attained service. That's bizarre. Why is that the case? Well, of course, we're dealing with an MM1Q, and it's going to be highly coupled to the fact that the service time distribution is exponential and therefore memoryless. So in some sense, when we think it's memoryless, it doesn't really matter which method we choose here. For instance, if we're using last come, first serve preemptive, if a job arrives and we're like, well, should I stop processing this one and start processing this one? Well, it doesn't really matter, because what's the expected remaining processing time here? It's 1 over mu, because it's memoryless. What's the expected processing time of the fresh job? 1 over mu. So this memoryless nature of it really doesn't affect it. It kind of gets washed out in the math. With processor sharing, you can think, okay, well, if there's 2 jobs in the system, like they're both being processed in parallel, okay, well, if there's 2 jobs in the system, they both will be being processed with exponential, distribution with rates. Well, not mu, but instead mu over 2, right? Because there's 2 jobs there. Well, if we take the minimum of that, we get an exponentially distributed random variable with rate mu. So processing them concurrently doesn't really change anything either. And you can use these arguments applied to the other ones as well. Well, I mean, that's just one of those things that, okay, for a very specific model, for an MM1, that might be the case. But is there anything else? Anything else we can observe? I mean, what happens if we look at an MG1Q? It can't be the fact that all these things are equal under an MG1Q. And you're right, they definitely are not. but some of them are. And let me say this. So an MG1Q, MG1, did the slash and the 1 backwards. Trying to remember this correctly, if it's just the distribution or is the expectation. I'll say the expectation. It might be a little bit stronger. You can check the textbook. An MG1Q has equal expected number of jobs in the system for all blind, non-preemptive policies. So we look over here. So if I'm using first come, first serve, if I'm versus last come, first serve, non-preemptive. So when a job arrives, I don't interrupt its service time. I wait for it to complete, but I still serve jobs in a last come, first serve order. Or if I'm using random order of service, the non-preemptive version, I can do that. So if a new job arrives, it doesn't interrupt it. But when a job leaves, I choose one at random. If my policy is blind, I don't use job size information, and it doesn't preempt jobs that are currently being processed, in an MG1Q, all blind, non-preemptive policies have equal expected number of jobs in the system. And we know what this value is because we analyzed the MG1Q under first come, first serve. That's another weird one. Here's perhaps the weirdest one. The number of jobs, the distribution for number of jobs, or maybe I'll just write this out explicitly. In an MG1Q, using processor sharing, the probability that the number of jobs in the system is n equals what? Equals rho to the n 1 minus rho. That should look familiar to you. What's that saying? Well, that's saying if I'm using, oh, what just happened to my marker? Something crazy. There. Okay, so what's this saying? Well, this is equal to the probability that n equals n in an in an MM1Q. But saying if I'm using processor sharing, the number of jobs in the system, the distribution of the number of jobs in the system is equivalent to that of an MM1Q. In other words, if I'm using processor sharing, the number of jobs in the system, the entire distribution is completely independent of the service time distribution. Wow. So processor sharing doesn't care about the service time distribution. All it cares about is, the first moment of it. Doesn't care about the variance. And an MM1Q using processor sharing will have the exact same performance with regards to, number of jobs in this system distribution as an MG1Q using processor sharing. Crazy. A very, very, at least counterintuitive result for me. Isn't something I would expect. Here's another one. And this is really like an odd one here. The expected number of jobs in the system for an MG1Q using processor sharing, so we can calculate that, equals the expectation. Why can we calculate that? Well, it's just the same analysis we've been doing, since maybe the 4th lecture or so. But this equals the expected value, and I hope I get this theorem right as well. Pretty sure it's true. Has the is equivalent to the expected number of jobs in an MG1 queue using last come first serve preemptive. So if I'm using last come first serve preemptive, I get the exact same expected number of jobs in the system as I do if I'm using processor sharing. Well, that also implies from Little's law that the expected response time of last come first serve preemptive equals the expected response time of processor sharing. That's really weird. Because you look at last come first serve and processor sharing, it doesn't even seem like they're close to similar. But it turns out that is a result, and maybe now you might be starting to get a little scratch in the back of your head. Maybe processor sharing isn't as fair as you originally thought, because, well, if I assume processor sharing is fair, and it's highly, highly related to last come first serve. I mean, it's not exactly, they'll have like different variances and different, shapes of the distribution, but the expectation is the same. Then it's like you're saying last come first serve in some way is inherently fair, which to a lot of you should almost seem like one of the most unfair policies you could have. But these are a bunch of, like I said, like a grab bag, bunch of results, very strong results, and I've like distilled it down, like a lot of proof and a lot of works just to a couple lines here. But yeah, it's crazy. And if you're interested in any of these results, they're all in the textbook, and the proofs for them are in the textbook as well, so you can check that out. But that gives you maybe a wider scope of ideas of how these different service policies, service disciplines are related to each other. Oh, there's another one. I guess I can read. No, I can do it up here. So shortest remaining processing time. So we're dealing with all the blind policies up here. Now I'm dealing with a non-blind policy. Shortest remaining processing time minimizes all moments of the response time distribution. What does that mean? Well, it shouldn't perhaps come to a shock that shortest remaining processing time minimizes the expected response time in an MG1 queue, but it also minimizes, the expected value of the response time squared, the expected value of the response time cubed, so on and so forth. It minimizes all moments of the response time distribution. So if all you're concerned about is your response time, and you have access to job size information ahead of time, use shortest remaining processing time. But that might lead into another issue we have to talk about, and we've been talking a little bit about fairness, but what might be one downside to shortest remaining processing time? And you've maybe talked about this before in your other operating systems courses, and I've talked to students as well, and they use the correct word here. But imagine you're a very, very large job. And you arrive to a queue using shortest remaining processing time. And you're a large job relative to the other jobs that arrive to the system. What happens? Well, you stand there, you're waiting for the people ahead of you to get served, and then a bunch of people are arriving during that period, and they're gonna, the chances are they're gonna have a size smaller than you because you're a very large job compared to them. And you keep on waiting, keep having these people arrive, and you're like, geez, this is getting crazy. What happens to the very large job? Well, you see starvation. That large job gets starved of resources. It's starved. And in some sense, you're like, well, yeah, but it's a large job, but it should have to wait longer. I agree. In general, you want, for a fair system, you want large jobs to wait longer than the shorter jobs, but it waits inordinately longer. Meaning, based off its size to response time or wait time, it's like an exponential relationship or something like that. It's not like linear. It's not like okay, if I'm twice the size, I'll expect to have twice the response time. It's not like that at all. Something very non-linear. And I don't know how YouTube does things behind the scenes, but something I've definitely noticed when I go to upload a video, if the video is like 10 minutes long, I will see like upload times and processing times of maybe around like 10 minutes or so. And when I go and upload like a 30-minute video, I see, processing times and upload times that are now like 2 hours long. And I'm like, what's going on here? Well, they're probably doing something like this. They're probably doing some form of, it might not be strictly shortest remaining processing time, but they're definitely giving a bias to smaller and shorter videos. And that's just the way it goes. But they're definitely starving larger resources. Okay, so that's like a brief overview of all these things. Which one do I want to use? Given a system, given an MG1 system, which service policy should I use? Is there a correct answer to that? Well, it depends what you want to do, first of all. Let's assume we're not dealing with non-blind policies. So let's just focus in on the blind policies. We don't know job size information ahead of time. If I'm operating an MG1 system, which one of these do I want to use? Well, I haven't given you enough information to really answer that question intelligently. So maybe the correct answer to that problem is, well, it depends. And I'd agree with you, it does depend. So imagine, for instance, I'm dealing with an MD1 system. Remember, I said I was dealing with an MG1, and MD1 is an MG1Q. Okay, well, if I'm dealing with an MD1, what might be a bad idea to do? What might be, a bad policy to implement? Would first come, first serve be a bad policy to implement? Maybe, maybe not. Let's zone in on this one. Least attained service time. So maybe jobs are deterministically served with 1 second apiece, right? So each job, like clockwork, will take 1 second to process. All right, so I'm processing a job maybe half a second, and a new job arrives. Well, using least attained service, I'm going to preempt the job that I was working on with this new job, because it's received 0 service. Does that make sense? Should I do that? Well, how long is it going to take to process that job that just arrived? It's going to take 1 second. How long is it going to take to process the job I'm currently processing? Half a second. So you think, well, if that's the case, I should be processing the job that's already there. And I'd agree with you. But that's an MD1 system. Is that always going to be the case? Well, the question that you might be asking is, okay, well, if I'm processing the current job, and it's been processing for T seconds, let's say, T time units, and a new job arrives, which one has a longer remaining processing time, or a longer expected remaining processing time? A fresh job, or a job that I know has been processed for a certain amount of time? Now you start to think about it. Well, we've been thinking about this stuff since the beginning, really. We just might not have been putting a spotlight on it. With an MM1Q, we're in like a very particular situation, because you say, well, the expected remaining processing time over here actually equals over here because it's memoryless. Okay, but can we find ourselves in situations where, okay, this job's being processed for 10 seconds. Maybe the mean processing time of a job is 5 seconds, let's say. I've been processing this one for 10 seconds, and a new job just arrived. Which one has the least or lower expected remaining processing time? Well, you might have a strong intuition that says the one that's been processed for 10 seconds has a lower remaining processing time, right? Well, because I put some effort into it, put some time into it already. And I put that time, therefore it's going to have less time remaining, right? I mean, I have a size, it has some size, I put in 10 seconds, I put in enough time, I should now expect to have less time remaining. There are some distributions where that's true, but there are many, many where it's not. And in fact, in real life workloads, That's far from the case. In fact, it's strongly the opposite. And to analyze that and to understand that, and then to understand why things like least attained service and preemptive last come first serve are appealing choices, we need to understand a little bit more about these distributions. Heavy tails, increasing and decreasing hazard rates, failure rates. That's what we're going to see in the next section. I'll see you there.